Hello students, how are you? Hope you all are very fine. Myself Taufikur Rahman and I am the physics teacher of Holy Child English Academy. Due to this critical situation, our school has arranged the online classes and we are taking the advantage of this technology by sitting at our home. Now I am going to start the second chapter, electrostatic potential and capacitance. Before we start the chapter, we have to know about the electrostatic potential. Okay, what is potential energy and where does it come from? So potential energy, about the potential energy, we have already studied it in class 11. Remember the law of conservation of energy. So in the law of conservation of energy, what is the statement? Energy neither created nor destroyed, it can be transformed from one form to another form. Okay, so in this case, suppose a ball is kept here on the table and if we push the ball, it will fall down. Okay, why it is falling down? Because due to the attraction of the gravitational force. Okay, so during falling, when it starts falling, its potential energy is maximum and kinetic energy is zero, because here the velocity is zero, it is in stable position. But when it starts falling, its potential energy is decreasing and kinetic energy is increasing. So before touching the ground, the potential energy is zero and the kinetic energy is maximum. So the total energy remains conserved during falling. Okay, at every point the total energy remains constant. Now, what is the measurement of the potential energy? Potential energy means, actually if we pick up the ball from the ground, we have to apply an external force. So a work has to be done by the external force to pick up the ball. Okay, so if we again replace it at your initial position, so the value of the work done will be mgh again. Okay, so this potential total energy, okay, so the work done is stored as a potential energy of the body. Okay, this work done by the external force against the gravitational force is stored as a potential energy of the ball. Okay, in case of electrostatic potential, I am considering a positive source charge plus Q is placed here. Okay, and two another points A and B within the electric field. At point A, Q0 test charge is here. Q0 positive test charge is placed at point A. Now, both the charges are positive, so a electrostatic force, that is repulsive force, is acting on the test charge Q0. Okay, and the direction of the force will be outward direction. So this is a electrostatic repulsive force. Now, if we want to bring this test charge from point A to point B, okay, so we have to apply a external force. A work has to be done due to the external force against the electrostatic repulsive force. So to bring the charge from point A to point B, that will be potential difference between the 2 points. Okay, so VB minus VA equal to work done to bring the charge from the point A to point B and by the test charge. Okay, so this is the expression of potential difference. Now the expression of the electric potential at a single point. So in this diagram, suppose the point A is located at infinity. Okay, so at infinity means the potential of the point A will be 0. VA will be 0 when A is placed at infinity. Okay, then we can consider VB equal to V. So the expression will be V equal to W by Q naught. Okay, this is the expression of electric potential at a single point. Okay, now electric potential at a distance r from a point charge. Consider a positive point charge plus Q is placed at point O and another point P. We have to find out the electric potential at point P, which is r distance away from the point charge. Okay, so the value of the electric potential at point P will be the amount of work done to bring a test charge from infinity to the point P. Okay, so for the calculation of work done, I am considering another point here, A and B. Suppose a positive test charge is placed at point A. Okay, so the electrostatic repulsive force is acting on the test charge and which is directed away from the test charge. Okay, so the expression of the electrostatic repulsive force by applying Coulomb's law, it will be Fe equal to 1 by 4 pi epsilon naught Q naught by x square. X is the distance between the point charge and the point A. Okay, now if we bring this test charge from the point A to point B for a small distance, which is dx, we have to do a work against the repulsive force. Okay, so this repulsive force, this work done, the amount of work done will be dW. It is F into small distance dx. Okay, so force into displacement is equal to work done. So the electrostatic force, it is acting outward direction and displacement is inward direction. Okay, electrostatic force direction is outward and the displacement, the test charge is displaced from the point A to point B. So both are in opposite direction. So the angle between the force and the displacement will be 180 degree. So here Fe dx into cos 180 degree. So this is minus Fe dx. So the value of the small amount of work done to bring the charge from point A to point B is minus Fe dx. Okay. Now to bring the charge from infinity to the point P, which will be, we have to do the integration. Okay, so total work done to bring the charge from infinity to the point R, it will be minus Fe dx. Okay, now put the value of Fe here and do the integration here. Okay, so no place to do. So W equal to here infinity infinity to R minus 1 by 4 pi epsilon naught Q naught by x square into dx. Okay, now here see 1 by 4 pi epsilon naught, it is constant, and Q naught, it is also constant, the multiplication of both the charges. So I am taking out from the integration. So 1 by 4 pi epsilon naught, it is Q naught integration infinity to R 1 by x square dx. Okay, so Q naught by 4 pi epsilon naught 1 by x square means x to the power minus 2 infinity to R, it is dx. So integration x to the power minus 2 into dx. So the integration will be here W equal to minus Q q naught by 4 pi epsilon naught. Okay, this is x to the power minus 2 plus 1 minus 2 plus 1 infinity to r. Now I am taking it out, so minus minus will be plus, 4 pi epsilon naught, it is minus 1, so it will be 1 by x infinity to r. Putting the value of the limit, 1 by r minus 1 by infinity. So 1 by infinity will be 0. So the final result of the work done will be q by q naught 4 by epsilon naught by r. Okay, this is the expression of the work done to bring the test charge from infinity to the point P. Now the expression of the potential, electric potential. Okay, so we know from the definition of the electric potential, it is V equal to work done per unit test charge. Okay, so put the value of the work done here. It is q naught by 4 pi epsilon naught r by q naught. So the final expression of the potential will be 1 by 4 pi epsilon naught q by r. So this is the expression of electric potential at point P, which is r distance away from the point charge q. Okay. Next, we are going to find out the electric potential due to a dipole. Okay, there are two positions, at an axial point and at an equatorial point. We have to find out the electric potential due to a dipole. Okay, so first we are going to find out the electric potential due to a dipole at an axial point. So first let me know what is electric dipole. Electric dipole is a system where two equal and opposite point charges are there. Okay, separated by a small distance. Two equal and opposite charges are there, and these two charges are separated by a small distance, but they are close to each other. So this system is called electric dipole. We can find out the dipole moment. So here dipole moment means P equal to, generally we can write the dipole moment is a vector quantity, so P equal to Q into 2A. Okay, so in scalar form we can write P equal to Q2A or 2QA. 2A here, the separation between the two charges. Now I am going to find out the electric potential. Consider a dipole system here. This is the minus Q and this is plus Q, which are separated by 2A distance apart. Okay, now we have to find out a electric potential at point P. Okay, so this point is r distance away from the midpoint of the dipole. Okay, midpoint of the dipole. Now, so we have to find out the electric potential for two charges here are there, plus Q and minus Q. So find out the electric potential at point P due to a positive charge and electric potential at point P due to the negative charges. Okay, we know the expression of the potential. It is 1 by 4 pi epsilon naught Q by R. Okay, so by applying this expression we will find out the electric potential. So electric potential EP at point P due to the positive charge, it is, suppose it is V1, so 1 by 4 pi epsilon naught. Okay, so positive charge plus Q and the distance is BP. Okay, so BP means R minus A, because from the middle point O, the OB is A and AO is A. Okay, so BP will be R minus A because R is the distance between O to P. Okay, So it will be 1 by 4 pi epsilon naught plus Q by Bp, that means R minus A. Now electric potential at P due to charge minus Q. Okay, due to charge minus Q is here. So this separation between the point A and B, it will be R plus A. Okay, so it is V2 1 by 4 pi epsilon naught minus Q by R plus A, that is actually AP. I am writing first is AP, then I will put the value of AP. Okay, 1 by 4 pi epsilon naught minus Q by R plus A. Within bracket it is R plus A. R plus A is the separation between the point charge minus Q and the point P, where we are going to find out the electric potential. Now the total electric potential at point P will be V equal to V1 plus V2. So put the value of V1 and V2 here. So 1 by 4 pi epsilon naught plus Q by R minus A here, plus 1 by 4 pi epsilon naught minus Q by R plus A. So I am taking the common Q by 4 pi epsilon naught. Q by 4 pi epsilon naught, it is R minus A minus, because minus sign is here, so minus 1 will be kept here, so 1 by R plus A. Now do the LCM. Okay, R minus A into R plus A, so it will be here R plus A minus R plus A. Okay, just see that simple calculation. So here will be Q by 4 pi epsilon naught 2A by R square minus A square. Okay, so this is the expression of total potential due to a dipole at point P, and this point is situated on the axial axis of the dipole. Okay, now electric potential due to a dipole at an equatorial point. Equatorial point is a point where the distance from both the charges will be same. Suppose in this dipole, I am considering here a dipole minus Q and plus Q. Separation is 2A. Now consider a point P is located here. So the distance from the minus Q charge and plus Q charge of the P distance of the point P will be same. It is root over A square plus R square. Okay, so here at point P we have to find out the total potential due to the charge minus Q and the charge plus Q. Okay, so I am going to find out this potential. So electric potential due to the positive charge plus Q at point P, it will be V1, so 1 by 4 pi epsilon naught, again it is, and plus Q by the separation between PB. So PB here, so you write here 1 by 4 pi epsilon naught plus Q, and PB means root over A square plus R square. Okay, it is a scalar quantity, and the PV distance if we consider this is a right angle triangle. Okay, so base is A and the perpendicular distance from the point P to the point O is R. Okay, so hypotenuse will be perpendicular square, root over of perpendicular square plus A square. Okay, so this is PB. Again, similarly, electric potential due to the negative charge minus q at point P, it will be V2. So V2 equal to 1 by 4 pi epsilon naught, okay, minus q by this one is AP, that is separation between the point charge and the point P is AP. So again it is 1 by 4 pi epsilon naught minus q, and AP is root over r square plus a square. Okay, now total potential at point P, it will be add up, because potential, electric potential is a scalar quantity. Okay, so both the potential will be add up. So the total potential at point P, so it will be add up, that is V equal to V1 plus V2. So V1 plus V2 will be, the value of the V1 is here, so put 1 by 4 pi epsilon naught positive q charge by root over a square plus r square, and here the value of V2 is this one. So I am writing here 1 by 4 pi epsilon naught minus q root over a square plus r square. Now see that 1 by 4 pi epsilon naught q by a square plus r square, this term are very common. Okay, so only minus sign is there. Okay, so both the term are equal but in opposite value. Okay, so a square plus r square minus 1 by 4 pi epsilon naught q by root over a square plus r square. So the resultant potential at point P will be 0, because both the distance are same. Okay, so here the potential at point P due to the dipole, it is 0. Where it is 0? At equatorial point. Equatorial point means the point, the distance of the point between the two charges will be same. Now equipotential surfaces and its properties. Equipotential surface, the name is telling the definition. Okay, equipotential means equal potential. Okay, so the surfaces where the potentials are same at every point on it, it's called equipotential surface. Okay, now here in this diagram I am considering one surface here. Okay, it is a equipotential surface of a point charge. So consider a point A and point B where the potentials are same. Okay, potential at point A equal to potential at point B. Okay, and another diagram here, just see that a positive point charge is placed at the center of the circles. These are the concentric circles. So if we consider this circle, okay, so on this surface of the circle, the potentials at every point is same. Okay, if we consider another circle, on the surface at every point the potential are same. So these surfaces are called equipotential surfaces. Okay, now the properties. Here the work done is 0, as the potentials are same on the equipotential surface. So the work done to bring a test charge from one point to another point, it is 0. How? Let me see. Suppose here a point A and B. So if a point charge is moved from point A to point B, the potential at point A and potential at point B, so the potential difference is VB minus VA, and it can be expressed by the work done, because I am taking Q0 charge from A to B, so a work has to be done. So it is WAB by Q0. Okay, now from this expression we can see the potential at VB and VA are equal. Okay, so this is 0. So WAB equal by Q0 equal to 0. That means work done is 0. Okay. So the work done equal to 0 due to the equipotential surfaces. Okay. Next, electric field is always normal on the surfaces. Here you see that the red marks are the field lines. Okay, line of force indicating due to the point charge. Okay, so the every line, it is perpendicular to the equipotential surfaces. Okay, now the third point, no two equipotential surfaces can intersect each other. No two equipotential surface, that means suppose this surface and this surface, they are not intersecting each other. If they intersect, so at the point of intersection, two value of the potential will be found. Okay, but it is not possible. So no two equipotential surfaces can intersect each other. Now solve some numericals. One numerical I have given here. Just see, 2 points A and B are located in diametrically opposite direction. Okay, of point charge of plus 2 microcoulomb at distance 2 meter and 1 meter respectively from it. Determine the potential difference between the 2 points. Okay, VA minus VB. So here given 2 points which are located diametrically in opposite direction of the charge plus 2 microcoulomb. Okay, the distance of the points from the charges are given here, 2 meter and 1 meter apart respectively. So we have to find out the potential difference between these 2 points. Let's draw the diagram here. Consider a point charge plus Q here. Okay, now 2 points A and B are located diametrically in opposite direction. So suppose A point is here and B point is in opposite direction. It is there. Okay. So the distance from the points, it is at point A it is 2 meter from the point charge and it is 1 meter. Okay, from the charge. Now we have to find out the potential at point A and potential at point B, then the difference. Okay, let's find out. So potential, electric potential at point A due to positive Q charge, it is VA. It is equal to, we know from the expression of the potential, it is Q by A. The distance it is given here 2 meters. So write here 2. Okay. And the value of the charge, it is given 2 microcoulomb. Okay. So first you write here value of the Q, it is 2 microcoulomb. So 2 into 10 to the power minus 6 coulomb. Okay. And the distance, suppose if it is O, then OA equal to 2 meter and OB equal to 1 meter. Okay, so you can write here OA, then we will put the value. So the value of 1 by 4 pi epsilon naught, it is 9 into 10 to the power 9. Okay, and the value of the charge, it is 2 into 10 to the power minus 6. Next, OA, it is 2 meter. Okay, now keep it here like this, and electric potential at point B due to minus Q charge. Okay, sorry, at point P due to plus Q charge. That means here we have to find out the potential at point B due to plus Q charge. It is VB. So 1 by 4 pi epsilon naught Q by OB. OB is the distance between the point and the point charge. Okay, so 9 into 10 to the power 9 into 2 into 10 to the power minus 6, and the distance of OB is 1 meter. So write here 1, so it is volt. Now find the differences between the VA and VB. Okay, so VA minus VB will be 9 into 10 to the power 9 into 2 into 10 to the power minus 6 by 2 minus 9 into 10 to the power 9 into 2 into 10 to the power minus 6 by 1. Okay, so I am taking the common of 9 into 10 to the power 9, 2 into 10 to the power minus 6, so it will be half minus 1. Okay, so this is minus half actually, so minus half into 9 into 10 to the power 9 into 2 into 10 to the power minus 6, so 2 will be cut, so the result will be minus 9 into 10 to the power 3 volt. Okay, the potential will be minus 9 into 10 to the power 3 volt. This is the answer. Now the second numerical, 2-point charges Q and minus 2Q are kept d distance apart. Find the location of the point relative to the charge Q at which the potential due to this system of charges is 0. Okay, so let me draw this system. Suppose Q is a charge here and minus 2Q charge is there. Okay, so it is d distance apart, so the separation between these two charges is d. Okay, now find out the location of the point relative to the charge Q. Okay, that means I am considering a point P here. Suppose it is A, it is B. So P is the point where the potential due to this system is 0. Okay, now find out the distance AP from the charge, actually Q. Okay, so let us assume that it is x. X is the distance of the point P from the charge small q. Okay, so the distance between the point P and minus 2q will be d minus x. Okay, now electric potential at point P due to positive charge plus Q. Okay, so it is V1 equal to, again it is 1 by 4 pi epsilon naught plus Q by AP. Okay, so 1 by 4 pi epsilon naught plus Q, AP means X. Again, electric potential at point P due to minus 2Q charge, it is V2. So I am writing here 1 by 4 pi epsilon naught minus 2Q by BP. BP is the distance between the point and the charge minus 2Q. Okay, so it is BP. So write the value of BP here, minus 2Q. BP is D minus X. Now the next is at point P the total potential of the system is 0. We know total potential of the system means we have to add up the individual potential. Okay, so it will be 0. Okay, so put the value of V1 and V2. 1 by 4 pi epsilon naught plus Q by X plus 1 by 4 pi epsilon naught minus 2Q by D minus X equal to 0. Okay, I am taking common here. So this points it will be 0. So after taking the common, Q by 4 pi epsilon naught 1 by x minus 2 by d minus x equal to 0. So 1 by x minus 2 by d minus x equal to 0. So LCM x into d minus x. So d minus x minus 2x equal to 0. Okay. You can pause the video and then note down it. So d minus x minus 2x equal to 0. Okay. So here d minus 3x equal to 0. So 3x equal to d. Therefore x equal to d by 3. So x equal to d by 3 means x is the distance between the point P and the charge plus Q. So what will be the answer? What will be the answer? The distance, actually find the location of the point relative to the charge plus Q. Okay, just write it is d by 3 distance apart from the charge Q. Okay, so the point, so write the answer. The point is located, the point is located at distance d by 3 from the charge, plus Q. Okay, so thank you student.